Kia ora koutou, no mai, haere mai. Welcome to lesson 20 for introductory physics. This lesson is on deformation and scaling. So what we're going to look at is the idea of objects not being rigid. So far, a lot of what we've talked about, as I mentioned in the previous lesson, has been solid objects, and we treat them as though they just are unchangeable. No matter how much force you apply, the object just accelerates accordingly. It never squashes or compresses or flattens out or does anything like that. So today we're going to throw all that aside, that sort of false idea of reality, and we're going to start talking about what's actually happening inside objects as they deform. So our learning outcomes for this lecture are to define elasticity and relate it to Hooke's law. We've already met Hooke's law, but we haven't really talked about what's going on inside an object as that happens. We're going to describe and apply the concepts of tension and compression. And then we're actually going to look at something called scaling, which is the idea of taking an object and getting an identical one that's twice as big or 3 times as big or so on, and looking at how strength and volume and mass and density and all of those things all change as you scale an object. So it's actually a slightly separate topic, which is why this lecture is called Deformation and Scaling. So to start with deformation, we are so far, we've ignored deformation. We've applied a force and that has resulted in an acceleration. But as we know, if you apply a big enough force, then you can actually break an object or deform it. So you won't always just get acceleration. You'll sometimes get this deformation. So we're going to think about that for a little bit. And the idea of deformation is simply the idea of forces inside the object. As we saw, objects are made of atoms. In a solid, the atoms are all connected to each other by those little bonds, and the strength of those bonds will determine how rigid that structure is. The more strength is in those bonds, the more rigid the object is going to be, and the harder it's going to be to deform it. By the time we get to a liquid, obviously, we have no fixed bonds. The objects, the atoms can move past any other atom in that liquid, and so we get very easy deformation. If you push on a piece of water, we don't call it a piece of water for that reason. We call it a bowl of water or a body of water. But if you push on some water, then that water just moves out of the way. It just deforms with very little effort. If you push on a soft object like a sponge or something with some elasticity to it, then it deforms fairly easily a lot of the time. And that's because, again, those bonds are made to be able to move and bend and stretch and allow us to deform that object. Or if you push on a rigid object like a block of wood or a block of concrete or steel, something solid, a rock, that does not deform very easily because it's got very strong bonds in it. So those bonds will determine how much deformation there is, but it's those forces that we're applying and how those forces relate to all the bonds between all the atoms as opposed to relating to the object as a whole. So when we deform something, such as a ball squishing, cars crumpling when they collide, or a table or shelf sagging under the weight of objects being placed on it, it is just the forces that are involved. It's the same forces that we've already talked about. We've talked about normal forces and the force due to gravity, and we've talked about forces due to pushing, which is all a collision is. A collision is just 2 objects pushing on each other. We've talked about all of those already, right? And it's the same forces. It's the same forces as before, but now we're thinking about what those forces are going to be doing inside the object. In the tennis ball, that first photograph, the tennis ball hitting the floor, there is a normal force on the ball from the floor, and there is a weight force from gravity on the ball downwards. And the ball had some momentum, so it had some kinetic energy, had some momentum downwards, and it needs a force to change that, to stop the ball from traveling downwards and give it, to start with, it's going to be elastic potential energy as the ball stretches, kind of like a spring. It changes shape, and then it'll turn back into kinetic energy, but going back the other way, the momentum will be in the opposite direction to what it was originally. So that's what's going on, right? And so far we've just talked about what the ball does to start with and after the collision. We did mention that there'll be forces to change it. We've even talked about elastic potential energy, but we've never yet talked about the idea of this change in shape, this deformation. Now, as with a lot of topics in this course, we're not actually going to go into too much detail. So we're not really going to get to a point where we can analyze a tennis ball colliding with something like that and figure out the shape and the changes that are going to occur. But what we will hopefully do is understand the cause of these changes, these tensions and compressions. That's what we're going to look at. So what happens after an object is deformed? So on the previous slide, we saw a tennis ball. After that bounces, it'll go back to its spherical shape. But those cars, I'll go back a slide, those cars are not going to go back to their normal shape. They're not going to return back to being perfectly car-shaped afterwards. That table covered in books and magazines, that's not going to just magically return to its original shape either. So what happens afterwards is determined by the properties of the material the object is made of. So some will return to their original shape and some will not. And that brings us back to Hooke's law, which we have already met, but now we're going to talk about Hooke's law in terms of any object. So elastic materials, springs are our great example that we use a lot because they are made to be elastic, or very close to elastic, as we'll see. So any material that returns to its original shape after a deforming force is removed is said to be elastic. So that is the definition of elasticity. It means that once a force is removed from an object, it returns to its original shape. Right? So there are plenty of objects that can be deformed, but only the ones that go back to their original shape after the deformation are what we call elastic. And so if you've got a bouncy ball like the tennis ball or any other ball, it will deform as it gets some force applied to it. But then when that force stops, the ball will return to its spherical shape. So it's an elastic ball. If you've got a blob of putty and you bounce that off a wall, it will flatten as it hits the wall, and then it will not really go back to being ball shaped, depending on the type of putty. As I said, springs are a good example. When you deform a spring, then let it go, it will return back to its original length. We design them specifically to have that function. If we have something that doesn't return, like the cars in that previous slide, then we call it inelastic. So an inelastic object doesn't mean it can't be deformed. It means that if it is deformed, then it won't return to its original shape easily. You might be able to force it back to its original shape or something close to it, but it won't do it itself. This is also sometimes known as plastic deformation, so elastic versus plastic. Everything in the universe is actually inelastic. There is no such thing as something that is perfectly elastic, right down to that atomic level. Doesn't exist. However, as with many topics in physics, there are a lot of scenarios where something is very close to elastic, and we can treat it as though it is elastic. So a lot of materials are very close, and we can pretend they're elastic because they're 98 or 99% elastic or even greater. But in reality, nothing is actually 100% elastic. Everything has a slight amount of inelasticity to it. So even a spring, you can press it and release it, then it looks like it went back exactly the same, but it might be a fraction of an atom's width less than it was before. And you do that again, and every time it might adjust slightly. And after the spring has been used millions of times, it'll be completely different than how it started. So everything is slightly inelastic, but most things, or a lot of things, we can assume, we can treat as though they're elastic. So this video here is just an example of a golf ball demonstrating its elasticity. You can see as it collides with the wall, it deforms significantly. You might not expect that of a golf ball, but they do deform significantly. But a short time after leaving the wall, you'll see that for a little while it's still sort of vibrating and oscillating, but a short time after it's pretty much back to being a sphere. So that ball is very elastic because it will easily return to its original shape. So I'm just going to play that again for you to watch. You can see original shape there is a nice sphere, as we expect for a ball. It collides with the wall, it gets very flattened, surprisingly flattened for a golf ball. And as it leaves the wall, it's still oscillating, it's still sort of smushing around a little bit because there's a lot of forces that have been applied. And so just like when you release a spring, it doesn't just immediately return to its original shape, it sort of oscillates around a little bit. The golf ball does that, but it does very quickly end up back as a sphere. So anything that will do that, anything that will deform but then return to its original shape is called elastic. But how much it deforms is determined by Hooke's law, by that spring constant that we talked about. Remember, F equals kx. The x is our deformation. For a spring, x is just a linear measure of its change in length, but for some objects like a golf ball, that linear measure doesn't really work, so it's a bit harder. We're not going to look at the equations for describing how much something like a golf ball deforms, but essentially it is still the same process. You could find the constant, you could calculate some changes in shape, but it would be very complex mathematics because we're now dealing with a three-dimensional ball-shaped structure, not just a nice linear spring. So you can still have an elastic object even if it deforms only a tiny bit, provided that tiny bit that it does deform, it returns back to its original shape afterwards. As I said, Hooke's law tells us the linear deformation for an elastic object. So we use Hooke's law, we don't go into any 2 or 3 dimensional problems. So if we've got a 1-dimensional elasticity example like a spring, then we can use Hooke's law. So we've already met this. There should be no surprise here. F equals negative kx, and you'll remember hopefully negative or positive kx, depending on whether you're talking about the force applied to the spring or by the spring. However, if you pull a spring too far, then it will stop being a spring as per the image shown there. If you pull it too far, it will deform. You surely, a lot of students have done this at some point with the, although I'm not sure you all use pens anymore, obviously not the same for computers, but for old-fashioned click pens with a spring in it, if you've taken them apart and found the spring and then you accidentally pull it too far and it stops being a spring, very hard to get it back to being a spring after you've done that. Once you reach that point, then you cannot get it back to, you cannot undo those deformations. They're no longer reversible. So that point is called the elastic limit. It's simply the amount of deformation an object can experience before it is permanently deformed. So even though we call a spring very close to perfectly elastic and we use Hooke's law to describe it, there will be a point at which if you apply too much force, it will deform the spring and then you will not be able to use Hooke's law anymore because it's just a bent piece of wire. I was about to say the last part of the first half. Remember, there's 2 halves to this lesson. One is on deformation and the second is on scaling. So the last part of deformation that we're going to look at is tension and compression. We've actually met both of these in a sense already. Tension we already talked about in terms of ropes and strings. We talked about them, the tension being the force that is transmitted through the object. Compression, we talked about the idea that you could compress a spring. We talked about the idea of pressure from a solid pushing down on another object. So it's related to those, pressure and compression. You'll see verbally there's a link there as well in terms of the word. So internal forces. Internal forces are what we talk about when we're talking about this change in shape, this deformation. So if you've got 2 identical springs as pictured here, this sort of gold colored spring, and you pull on the 2 ends and you push on the 2 ends of the springs, then both of them are experiencing forces of 0 newtons, net force, I should say, of 0 newtons, but we expect very different things to happen. So we need some way to talk about the difference in these 2 cases. On the left and on the right, both of those springs have net 0 force, but they are very different scenarios because we know that the spring is elastic. If that was a rigid body, as we talked about in all our previous lessons in the first half of the course, if that was a rigid box and we were applying 2 forces to it, then in both of those scenarios we would say net force 0, nothing happens. Both scenarios are pretty much the same. We have a box at rest. However, because we've got something that can deform, those scenarios are not the same anymore. We know that different things are going to happen. And we know specifically that the left spring is going to get longer and the right spring is going to get shorter. So that one that gets longer, that is what we call tension. When a force is attempting to stretch something, we call the object as being in tension. We say it is in tension. So springs are in tension when you hang a mass on them. Ropes are in tension when they are supporting something. So if you hang something off a rope, that's in tension. But solid objects that are elastic can be in tension as well. So any solid object that can stretch slightly is in tension. And actually, it doesn't even have to be elastic. I shouldn't really have said that in the slide there. Any object that has forces that is trying to stretch it is called under tension. Elastic objects will stretch slightly when they're under tension, but any object can be under tension. So how much they stretch depends on their elasticity, but anything can be under tension. Compression is exactly the opposite, as you may have guessed. When a force is trying to squash something, then that object is under compression. So the spring, you try and squash it with 2 forces, it will squash because it's a spring. That spring is now under compression. Ropes can't be under compression along their length. You can't use a rope to push something. You can put a rope under compression if you squash it widthways, but then it's just like any piece of material. It doesn't need to be a rope specifically. But of course, any solid object can be under compression. If you have forces that are trying to squash it, it's under compression. Again, if it's elastic, then that object will compress slightly, it will deform slightly, but you can have very rigid objects that can still be under compression and barely noticeably deform. So tension and compression is simply whether the forces on the object are trying to squash it or stretch it. We talked about the idea that everything is made of atoms. We talked about solids being made of atoms that are all bonded to their neighbors. And now we've talked about the idea that these solids can actually change if there are forces applied to them. So the more elastic it is, the more it will change. So let's just think for a moment about the atoms inside the structure and what's going on when we apply the forces there. So this diagram on the left, we've got 4 atoms. We're only looking at 4, even though there'll be billions in any object that we're actually considering, but we're just thinking about 4 as an example. If you've got 4 atoms, and then you squash downwards on them, or you compress them, then you'll get that bottom left image where the 2 on the left and 2 on the right have moved closer together. There's no sideways force here, so the distance horizontally is still the same. That vertical distance is decreased because we have some compression being applied to that object vertically. You'll notice that the bonds between the atoms are drawn here as springs, and that's because they do follow a similar law to Hooke's law. You can actually use Hooke's law for a certain amount of this bond deformation. We're not going to get into that in this course. We're not going to go any further, but it does work just for you to think about the atoms as being connected by springs in a solid. If they were really stiff, solid springs, then they're not going to compress much, and that object is not going to be very elastic. Right? You can apply huge forces and the object won't compress much. So if you imagine a block of concrete, it has really, really thick springs between every single atom, then it's not going to be able to compress much. In reality, those springs are the bonds between the atoms making up that object. But they are very strong, solid bonds, and so they cannot, I shouldn't say solid because we're talking about solids in other sense, but they're very strong bonds, and so they cannot compress very easily, so the solid block of concrete does not compress very easily. But in something like a block of rubber, like an eraser that you might use when you're working, the bonds between those atoms are pretty stretchy, and so you press down on that, and the rubber can actually bend and squish quite happily. Same thing with tension. If you stretch an object, try and stretch it, I should say, then the bonds between the atoms will determine how much it can stretch. If they're nice, easy, stretchy bonds, then the object can stretch, just like rubber bands or other forms of elastic. If you've got a nice solid object like a block of concrete or a brick, then you're not going to have a good time trying to stretch it out because the bonds between the atoms do not want to stretch out. I've just noticed now that some of that text is hidden by the image, unfortunately. I can't edit, I could edit that right now, I'm not going to, but it's just what I've been talking about. If the bonds between the atoms are stretched, then they're increased, then we have tension, and if they are decreased, if they're squashed, then we have compression. Remember that we talked about elastic potential energy. We talked about springs having elastic potential energy when you squash or stretch them, because the spring, when you release it, will then use that energy to turn into kinetic energy as it tries to return to its original length. That is the same for any elastic object. Those chemical bonds between the atoms making up the solids will store elastic potential energy in them if you deform the object. So it doesn't have to be a spring to contain elastic potential energy. It just has to be any elastic object. Remember that elastic doesn't mean it stretches or compresses a lot. It just means that if you do stretch or compress it, it will return to its original shape when you release it. So you might have something that's very solid and seems very solid, but is actually elastic in the sense that when you apply a force, it deforms only a really tiny, tiny amount. But when you release that force, it returns back to its original shape. It moves back that tiny, tiny amount. But if it does that reliably, it moves back to exactly where it started. Even though the deformation is tiny, that's still an elastic object. Whereas a more highly elastic object will deform more, but then still return. So remember that difference between being elastic versus inelastic versus the amount of elasticity in terms of the strength of the spring constant, right? So the higher the spring constant, the less it will deform under the force. But if it's elastic, it will still return back to its original shape, even though it had a small deformation, right? So there's a fair bit to keep track of in terms of thinking about these. As I said, we're not going to go too far into it. We've met Hooke's law. We know how to use Hooke's law. That's kind of all we're going to do. But for the rest of this topic, for the rest of thinking about objects and deformation and tension, it's mostly qualitative, not quantitative. Inelastic material and energy. If you have an inelastic material and you apply some energy to it, you do work on it, just like we saw with a spring, you do work and it deforms, the spring stores that energy. But if you have an inelastic material, so if you've got something and you do some work on it, so maybe you've got a cardboard box and you squash the box completely, you've done work on that box. But when you release it, it doesn't return to its original shape. So it's not storing any kind of potential energy, because when you let go, it doesn't suddenly spring back to what it was, unless you've got a special trick box. But what you do have is work being done on an object. So it has to go somewhere. That energy has to go somewhere. Remember, we have energy conservation. We can't create or destroy energy. So where is it going? Well, it's spent on things like breaking bonds, forming other bonds, heating up atoms, things like that. So the energy is used in ways where it can't be easily recovered and converted back to kinetic energy, as it does with elastic potential energy. So there's no stored energy in the object in the same way there is for springs and elastic objects, but there are still forces. So as I said already, elasticity can be a little bit confusing because we've got to keep track of two different things. We've got to keep track of whether an object is elastic or inelastic, and we've got to keep track of whether an elastic object, how elastic it is in terms of its spring constant, right? So how elastic it is in terms of whether it deforms and goes back to its original shape perfectly. So that's the elastic versus inelastic scale. Or how elastic in terms of the spring constant. And we'll say how elastic for both scenarios. So I might say, how elastic is this? Meaning, is it elastic or is it inelastic? Or I might say, which is more elastic? Meaning, which one has the higher spring constant, or sorry, I should say lower spring constant, and will deform more when you squash it. So you've got to be very careful to interpret the question or whatever you're trying to understand, and make sure you are on the right page about what you're looking for. Are you looking for whether the object returns to its original shape? Or are you looking for how much it deforms with a given force? And we've also, of course, met the idea of elastic collisions. So an elastic collision is actually the same idea here as the inelastic versus elastic objects. Two elastic objects, if they collide, will collide elastically, because they might deform as they collide, but then they'll go back to their original shapes as they come apart. And so that means all the energy that goes into deforming them as they collide is stored as elastic potential energy and then returns to kinetic energy as they separate. And so because we've got that energy conservation and the energy hasn't been used to permanently deform anything, that means the energy must go back into kinetic energy, which is why for elastic collisions, we have conservation of kinetic energy. For inelastic collisions, then we've got inelastic objects, at least one of them must be inelastic. And the energy, as we just talked about, is going to go into deforming the bonds, changing the shape of the object, heating it up, doing things like that. So an inelastic collision simply means that at least one part of one object involved in the collision was inelastic. That's all the collision terms mean. They mean the same thing as we've just talked about here. What about bending an object? We've talked about squashing or stretching, but what about bending? If you bend an object, then think about how long it is. The inside curve here is shorter than the outside curve. That middle, if you draw a dotted line along the middle, then that will be the original length of that object, whatever it was. So that means you've got the outside being stretched, but the inside being compressed. So when you bend an object, you're actually getting, causing part of it to be compressed and part of it to be under tension. So you actually get both scenarios occurring at once when you bend something. As I said, the middle layer will still be the original length. So that middle layer is what we call a neutral layer because it is not under tension or compression. Right? It's the bonds between all the atoms along that plane, along that line, are still exactly the same length as they were to start with. They haven't been stretched or compressed. And of course, the bond doesn't care if it's this way or this way. It doesn't actually matter. What matters is that these bonds between this and the next layer up will have changed, and that's what's causing the tension and the compression. But the ones along that neutral layer itself, they're all still the same length, so they don't really care that the object has been bent. So we call that the neutral layer. For stone, this is just a little bit of a sidetrack almost. When we're talking about constructing things, if we're using stone, stone breaks easily under tension. Under compression, stone's very strong because the atoms are being forced closer together and they remain very strong. But when you have stone or concrete under tension, then those bonds become quite weak. They're stretched to their limit and they break quite easily. So stone slabs are not very common as a long supporting object. So often you'll see wooden beams inside a stone building, because wood is actually stronger under tension than stone is. So stone long slabs, not very useful. That diagram is obviously exaggerated, but the idea is that a long slab of stone will sag downwards, therefore it's under tension, as we just saw when something bends, the outside is longer, therefore it's under tension, and then it'll break more easily. So stone is not a good building object. But if you can build an arch, then every block in that arch is actually under compression. They're all pushing against each other. So they're all under compression, and that will result in a very strong frame. So an archway is a very strong structure. They actually become more strong than they would if it was just the blocks sitting there on their own, because here they're now under compression, so they're stronger. If you are designing something to support a load such as a bridge, then a parabola is the best shape for the arch. So that is the Sydney Harbour Bridge. There you can see a nice parabola. It's the same shape as we had for projectile motion. We're not going to talk too much about the mathematics or reasoning behind that. Just a nice little fact that that parabolic shape comes back in with archways. So if you look around at bridges, any kind of arch bridge like the Sydney Harbour Bridge, they will generally always be parabolas because they are the best shape. They're the strongest shape for supporting a load. However, if you've got something that's just freestanding, so it's not supporting a load, such as this structure, I forget the name of it, somewhere in the United States, I believe. If you have a structure like that, that is not supporting a load, it's just freestanding, then the shape that is the strongest is actually known as a catenary or quaternary. I forget the exact pronunciation, but it doesn't really matter. The thing here is the shape that is made is the same as that when you take a piece of rope or a string and you just hang it by two ends and it hangs like that. That's not a parabola. It's the slightly different shape, and that turns out to be the strongest shape if you've got an object that is just trying to support itself. So if you're building an archway like that that's just purely decorative, then the catenary is going to be your best bet. Domes, we're not going to talk about them much, but they're just a three-dimensional arch, basically. An arch is just a two-dimensional curve. If you rotate it around itself and trace out that path, then you've got a dome. So that's all a dome is. So same thing applies. If you are building a dome that something is going to be on top of, then you want a parabolic dome. If it's just purely decorative, like a ceiling or a roof, then you want a catenary-based dome. An important consideration would be if you are in an area where it snows and you're going to get a lot of snow build up on the roof, then you would want a parabolic one, because now it's going to be supporting a load and you're going to need it to be able to accommodate that. So that's the first half of the lesson on deformation. The second half will be a little bit shorter, but it will be on scaling, which is not really anything to do with what we've just talked about. It's its own little topic. So scaling, what are we talking about for scaling? One of the big things that we talk about is strength of an object. We're going to talk about quite a few more, but we're going to start with strength. So if we've got a little matchstick and we want to break the object, we want to take a matchstick and snap it, just like I've drawn there. What you need to do is you need to break the bonds between every atom along that breaking line. So draw a slice through the matchstick. You need to break all those bonds between all those atoms. That's how you will break something. There will be weaker points and stronger points. When you break wood, you'll often find that it breaks along sort of lines that are already existing in the wood between the cell structures and things, rather than ripping cells apart. It will break between them. So it'll choose the weakest point, but you still have to break bonds along every part of that object. If there weren't any bonds there, then the object wouldn't be held together at all and it would be two separate objects. So it has to have some bonds there to start with, and you have to break them in order to break the object. So if you take a matchstick that is doubled in every dimension, right? So we've got here the original matchstick, and now we've got one that's twice as wide, twice as tall, and twice as long. Twice as long doesn't matter, right? Twice as long is irrelevant because when we break it, we're just breaking it through one plane, but it's twice as thick in both dimensions. And that means the area, the number of bonds that we have to break, is going to be bigger. How much bigger? Well, you can imagine stacking 4 of our original matchsticks together, and that would have the same thickness as our one big matchstick. So ignoring the fact that we've just got 4 individual ones sitting there, the number of bonds you're breaking will still be essentially the same, because if you slice through it, the area that you're slicing through is the same in those 4 stacked up versus that one bigger matchstick. So it would be 4 times as hard to break. You've got 4 times as many bonds to break, you need to apply 4 times as much effort, right? So we're not really defining strength in any real formulaic sense. We're just using the concept of strength, but it would be 4 times as hard to break. As I said, you can see that by stacking 4 up, but what about if we go to tripling? So we're now 3 times as thick. As you can see, you would need to stack 9 matchsticks together to make one block that's as big as a tripled matchstick. So tripling in the linear dimensions is making that cross-sectional area 9 times as big and therefore 9 times as hard to break. So the strength has increased 9 times, even though the linear dimensions have only increased 3 times. Let's talk about surface area now. So we've seen strength. What about surface area? If we talk about surface area, then we can do this formulaically because it's a simple equation to figure out the surface area. Anything that's cuboid, so that matchstick is just a rectangular prism, therefore it's got 6 sides, and we can just figure out the area of each side and add them all together. So we've got 2 little squares, which are just t squared, and we've got 4 long sides, which are t times l. So our total area is 2t squared plus 4tl. For the doubled matchstick, the little squares on the end are now 2t all squared, which becomes 4t squared, and we've still got 2 of them. And the long sides are now 2t times 2l, which is 4tl, and again, we've still got 4 of them. So we can take those 4s, if you look at that equation, that second line, we've got 2 times 4t squared plus 4 times 4tl. We can take the 4 from each term and factor it out. We get 4 times 2t squared plus 4tl, which is 4 times that original area A1. So that means we have a surface area that is 4 times as big after we increase the linear dimensions by a factor of 2. Another way to look at that would be that it's 2 squared. And hopefully what you've picked up here is when we talked about changing units, we talked about the idea that if you had 2 dimensions, then you needed to multiply by your unit conversion twice, not just once, right? So you had centimeters squared, you had to do it twice. It's the same sort of idea here. If we've got a linear dimension that we're changing by some amount, so in this case 2, then we're looking at the area that changes as a result of that linear dimension. Then that linear dimension is 1-dimensional, the area is 2-dimensional, so we've got to multiply by it twice, or by 2 squared, not just by 2. So it's the exact same sort of concept. It's just this reminder that you have to think about things in 2 or 3 dimensions, not just in 1 dimension, as we're used to doing with some basic math. So by doubling the linear dimensions, we have quadrupled the surface area. And you remember that we also quadrupled the strength. And you'll also remember that I said strength is like an area because you have to slice through in the area of that object. How many bonds there are in that cross-sectional area is how many bonds we have to break. So what we're hopefully starting to put together is the idea that anything to do with area is going to be related to your linear scaling factor squared. Right. What about if we triple it? If we triple the object and look at the surface area, the exact same math, so I'm not going to read it out again, but do follow through that math there. By tripling the linear dimensions, we see that we have 9 times as much surface area. And of course, 3 squared is 9. So we've still got the same rule. If we increase the linear dimension, so our scaling factor is 3, we make each linear dimension 3 times bigger, then any area-based property, so the surface area or the cross-sectional area, which was related to the strength, is going to increase by 3 squared, or 9 times. So when we double, we get quadruple. When we triple, we get 9 times. And as I said already, this slide is just in here to remind people, and especially if you're not watching the videos, then you'll be able to see this that I've been commenting on. The idea that the cross-sectional area is related to area, just like surface area was. So they're both area related. So in general, we've looked at 2 times and 3 times, but in general, if you make something x times bigger, so our linear scaling factor of x, then the area properties, so that's both surface area and the strength, are going to be changed by the square of that factor, so x squared. But it also depends on anything that depends on the area. So cross-sectional area, like the strength of the object, but anything that depends on area. So you might be talking about a solar panel, and you might be scaling the dimensions of the solar panel. Then if you scale the dimensions by X, the amount of sunlight it catches depends on the area of the top of that solar panel. So that would scale with X squared. So anything that depends on area is going to be related by X squared if the linear dimensions scale by X. What about volume? Volume is three-dimensional. As we saw when we were talking about unit conversions with 3 dimensions, we had to do it 3 times, so that might give you a bit of a hint, but we'll work through the maths here. The volume is just T times L. Hopefully we're all familiar with calculating the volume of a rectangular prism. If we double that matchstick, then we have 2T times 2T times 2L, which is 8 times T squared L, which is just 8 times our original volume. So if we doubled our linear dimensions, our volume increased by 8 times, and 8 is just 2 cubed. So for area-based properties, we saw that it went up by 2 squared, and for volume, it goes up by 2 cubed. So doubling, we get 8 times as much. Same thing, linear, if we linear, we triple, then volume, we multiply by 27, which is 3 cubed. So 2 cubed or 3 cubed, so our linear factor cubed. So just as we saw with the area-based properties, the volume goes up with cubed instead of squared. But if we know the density of the object hasn't changed, so if you have a matchstick that's some small volume and then you triple or double, doesn't matter, if we double the dimensions and therefore 8 times the volume, if the density is the same in the new matchstick, the big one as it was in the original one, then that means that the mass is going to be 8 times as much as well. Right? If the volume is now 8 times as much and the density is the same, then the mass must be 8 times as much as well. And the same with the tripling, you would get a mass of 27 times as much. That is assuming the density is constant, right? And that's something we would assume if we're making matchsticks, because we'd make them all out of the same wood. So the density should be fairly consistent. So we saw that area-based properties were X squared, and now we've seen that length and volume, length going up by X means volume's going to go up by X cubed. So anything that depends on volume is also going to go up by X cubed, just like we saw with mass. Right? If the density stays the same, then mass is going to be going up by X cubed. That is, as I said, assuming the density is constant. You don't need to write that. It's one of those implicit assumptions. If we're talking about making a bigger matchstick and what that would do to the volume and the strength, then we would assume the density is constant, because we would assume that you're going to make it out of the exact same wood as the original matchstick. However, you do need to be careful, because there are some scenarios we'll talk about. I believe I included one in the worksheet where density isn't actually going to be constant. If you've got a sponge and you squash the sponge, you've changed its volume, but you haven't changed the mass, you've increased its density though, because you've now got that same mass in a smaller volume. So you do have to think about the scenario a little bit and think about whether or not that is a valid assumption. We will normally, as I said, implicitly assume it, but there are scenarios where you need to realize, hey, that's not actually happening this time. Scaling is this whole study of what we've just been talking about, the idea that you can change linear dimensions and seeing what happens to the other properties of the object. If you change a linear dimension by a factor X, then the surface area and the strength will go up by X squared, and the volume and the mass will go up by X cubed. That is scaling. That's what we're talking about for scaling. And this is the idea of scaling can be used a lot. You might build a bridge, a realistic bridge out in the real world for trucks and cars to use, and you can figure out all the maths and everything. And then if you build a scale model of that bridge, it's not going to have the same relative performance capabilities. Right? A smaller scaled bridge, even though the linear dimensions might say you make 1/2 scale, the linear dimensions will change by 1/2, but the strength will change by 1/2 squared, which is 1/4. So it will now only be 1/4 as strong as the big one, even though it's only 1/2 as big. So there's very real world practicality things to consider. You can't just take a big bridge and scale it down to fit into a smaller space, because you will change its strength as you're doing so. And just to ruin a few movies, if you scale an ant, make a giant ant, same thing applies to giant spiders. It's a common sort of trope, a common thing to do in movies is to scale up monsters and things. then you may expect it to become very strong, and indeed it will become very strong. Let's say we have a 1 centimeter ant and we scale it up to be 1 meter. So it's not a super giant ant, but it's now 1 meter long. That ant is 100 times bigger than it was to start with. That means it will be 100 squared, or 10,000 times stronger. So this ant is now 10,000 times stronger than it was before, but its mass, assuming its density is constant, well, the same density as it was to start with, excuse me, then its mass will increase by a factor of 100 cubed. So it will be 1,000,000 times as heavy. So it might be 10,000 times stronger, but it's now 1,000,000 times as heavy, and the ant probably won't even be able to lift itself off the ground. So this is, as I said, assuming a constant density. In a lot of movies, obviously, they're magically scaling up objects, which breaks all sorts of laws of physics anyway. So why not break that density one and say that as the ant scales, it retains its original mass, or perhaps its mass only scales, its density scales as well, so that it only ends up to be the same strength and weight scaling ratio or something. So obviously you can work your way around it, but they often don't bother in movies. Volume and surface area is another common one. So this is the idea that if you change the volume of an object, then its surface area must change as well. And as we saw, when you increase linear dimensions, surface area increases, but volume increases more quickly. Volume increases faster than surface area does. So as the volume increases, this ratio of surface area to volume decreases. If you increase the volume of something by a factor of y, then you'll increase the surface area of that object by a factor of the cube root of y squared. You don't need to remember that formula, right? Just all the formulas we've already talked about, the x squared and x cubed, which aren't really formulas, but those scaling ratios, you do need to know those. You don't really need to know this one, but it can be handy because it can be a little bit quicker. It's basically a shortcut. It says if the area goes up by y, then y must be equal to x squared. So if you take, the volume of something goes up by y, then x must be y, x cubed is y. Sorry, I'm just getting my numbers back to front. X cubed is y, therefore the cube root, and my words back to front, cube root of y is going to be x, and then you square that to get the scaling factor for the surface area. So the volume and surface area do change as you scale objects, and they change at different rates, just like the mass and the strength of that ant change at different rates. And indeed, that's why if you're going to be peeling potatoes for dinner, then you want to get large potatoes, because you'll get the same volume with less surface area than if you have a whole bunch of small ones. You'll have a lot more surface area and thus a lot more peeling to do. But if you're not peeling them and you're going to roast them with skin on, then you like the skin, then you might want to have smaller potatoes so you get more surface area per volume. So everyday decisions like that can be affected with this concept of volume and surface area ratio. If we're scaling something down rather than scaling it up, then these factors are all exactly the same. We're just now dividing by instead of multiplying, but that works exactly the same if you say that x is 1 over z. So I'll let you read through this slide rather than me read it all out, but I already hinted at this when I talked about making a bridge smaller. So multiply it by a factor of 1/2, then the strength will go down by 1/4. Or go down to 1/4. So that's the same as divide by 2, then divide by 4. Same idea. It's just whether or not you call z your division factor or x your multiplicative factor, which one you're talking about. That's the only real difference here. And that's the end of this lesson. As I said, it was sort of 2 different parts. We had tension and compression, and then we had the idea of scaling. So 2 sort of concepts to get your head around in that lesson.